Welcome back. We are discussing section 3.2, concavity and points of inflection. In this second video, we're going to tackle, it's a little bit amorphous here, but locate and examine inflection points and apply the second derivative test for relative extrema. So we're going to do one example of this, and in the next video, we'll follow up with an additional example of the second derivative test. So let's get ourselves to inflection. So, inflection point. So new piece of terminology. An inflection point is to the second derivative as a relative maximum or minimum is to the first derivative. That makes no sense whatsoever and sounds like a horrible SAT question. So what I mean by that is an inflection point is a place where the concavity of f changes, and thus by definition, since the concavity is changing, that means that f prime is switching from being increasing to decreasing, or vice versa. F prime is switching from decreasing to increasing. So this is where the derivative itself is changing direction. So that's this notion of curvature. So an inflection point is basically just a place where the curvature of the graph changes. So just to pick a nice picture to work with, the claim is that this function has two inflection points. So one thing we could consider basically is that over here on the far left side of the graph, if we're thinking about this fitting a parabola to the picture kind of deal, there'd have to be an upward opening parabola in order to fit along this left side. And then somewhere along the line, though, it changes, and here in the middle we've got this inverted, this upside down looking parabola. And so somewhere in there, the concavity changed. And to identify that, it's kind of hard to visualize this, or at least to pick a point with great accuracy. But if I like to just put my finger down or put a pencil on the graph and see if I can tell, okay, does it really look like it's curved to the left and curved upward on the left side and curved downward to the right side at that point? And if not, then I sort of scoop my pencil a little bit and see if I can eyeball that a little better. But at any rate, somewhere in here, it switches from being curved up to curved down, and so a point of inflection is somewhere in the midst there. And this happens one more time. So over here on the far left side, we have a graph that's curved upward, and somewhere in the middle here, it switches from curved down to curved up. So we have our second inflection point somewhere in that vicinity, where the graph changes from concave down to concave up. Okay. So the second derivative test is a way to look at the function and determine classify the critical points. We already have a strategy for this, the first derivative test, but the second derivative test accomplishes the same goal in kind of a different manner. And basically it says, take the second derivative and evaluate it at some critical point that you know of. So if we do f double prime of some number and we get a positive value, then that means that we're supposed to have a relative minimum at that value. And the way we're supposed to think about this is that if there are basically three possibilities, there's a curved up, there's a curved down, and there's this saddle point as far as what can happen with a critical value. If I get that the function is curved up there, then I can be pretty sure that this critical point is sitting at the bottom of a little valley. And thus we have the relative minimum case there. If the second derivative is negative, on the other hand, then that's telling me that we have a relative maximum because we're in this situation where the function is curved down. So if there's going to be a critical point, it's going to be sitting on the top of this little situation. So there is another possibility. You notice that if the second derivative is equal to 0, that's more like these saddle point possibilities, but actually what it really means is the second derivative test is inconclusive. It doesn't give us any meaningful answer. So we'll put this to work, find and classify critical points of this function. And we'll specify that we'll try the second derivative test out just to see how it goes. Okay, so first we have to find critical points, again, using the job interview analogy. Critical points are all of our candidates for the positions of relative max, relative min. And so by finding critical points, we're getting our applicant pool. We're figuring out everyone who could get the job, but we don't actually know until we do more searching who's going to get what job, if any. Okay, so finding critical points is the derivative set equal to 0. Again, there is this one other thing we can check, the derivative being undefined. We'll follow that up next. So most of our solutions are going to come from derivative equal to 0, though. So we got some quotient rule action. So here's our low, d high, derivative of x squared, and then high x squared times the derivative of x plus 1, which is just 1. X plus 1 squared on bottom. Okay, and then because we're trying to take the derivative and set it equal to 0, we'll replace f prime with 0 and then attempt to solve. Well, okay, so this denominator piece is never, well, it will never help us make this fraction 0. It can make it undefined, but that's not really very much fun. So we can multiply basically both sides of this expression, both sides of this equation by x plus 1 all squared, and it won't actually impact our solutions. That's true as long as we don't get an answer of -1 from this mess, but we don't, so things are good. So really, we can just solve numerator equal to 0. With a little factoring, pull out an x from each of those, so we're going to get a couple of solutions, 0 or -2. So then the other half of this, we figured out where f prime is 0. We should also check that our derivative, where our derivative could be undefined. So the thing that could go wrong with this is that x could be -1. And in which case that would be division by 0, which certainly is undefined. But the thing is, the original f function also has an x plus 1 in the denominator, so it's also undefined at x equals -1. And we're right back in that category of running into a situation where, sure, the derivative is undefined, but the original function has no point there. You cannot be a critical point of f unless it's actually a point on the graph itself. So since f is undefined at -1, there's no critical point there. Okay, so our only job candidates here are -2 and 0, but we still don't yet know which roles they're going into. So the second derivative test is what helps us determine who's a max and who's a min, or maybe we don't get any information, but we'll try to reduce the number of those cases because they're kind of annoying. So the second derivative says start with the derivative function and take its derivative one more time. So we've got our quotient rule deal, low d high. So derivative of the top is 2x plus 2 minus high d low. And the derivative of the bottom is a little more exciting. We've got some chain rule action, 2 times x plus 1 to the first power. So really, if we really wanted to, we could put a little first power on this. And then chain rule of the inside, well, but derivative of x plus 1 is just 1. So nothing super exciting get tacked on there. You sort of get rewarded if you forgot about chain rule there. You'd still get the right answer. Okay, so we could expand this thing, but there's actually a very convenient simplification that we should take care of first, and that is x plus 1 is a factor of all the terms. So if we pull x plus 1 out, it's going to reduce the overall monstrousness of this equation. Well, this derivative expression. So what we have left is still some x squareds, but we're not going to end up with x cubes, which is nice. So expanding out the top, now we actually distribute everything, combine some like terms. Notice that a lot of this stuff goes away. We have 2x, 4x, and then minus 4x. And then negative 2x squared and positive 2x squared. So all we're left with in the top is this 2. So there's our second derivative function. Now it's our job to evaluate this. So the second derivative test says, find the second derivative, plug in the critical points. They have to be critical numbers. We can't choose just any old x values and get some good information. This is only a valid test if we use numbers that cause the derivative to be 0. Okay, so now we're going to classify. So we take x equals -2. That was one of our critical points. Plug it into the second derivative, and we get -2. So remembering the pictures that go along with this, if the second derivative is negative, then this graph is curved down. That must mean that any critical point is a relative maximum. And that's our conclusion for this. It's less than 0, so we can say that there's a relative maximum at x equals -2. So our other case, x equals 0. Again, f double prime here is a positive number. And so we're looking at the upward curved case. So if we have any critical points of it, it's going to be a minimum of that function. So just to take a look at the graph, to confirm what it is that we're up against. Here's our original function. Here's a sketch. And we could be using this from the beginning just to give us some perspective. We ought to be able to tell that there are a couple of extrema here, although it might be, if we guess at whole numbers, we do pretty well. But if this had been negative 1.95 instead of negative 2, I'm pretty sure I wouldn't have been able to tell just from just glancing at this graph. So the calculus helps us nail down the exact values that are important to us. But the general shape of the graph ought to give us a lot of information about what to expect. So we should have expected two extrema, two critical points, because there's two places where the derivative goes to 0, horizontal tangent lines. And then minimum at 0, as claimed by our test, looks reasonable, and a relative maximum at negative 2 also seems reasonable. This is a really good example of a case in which it doesn't make sense to simply plug them into f and see which number is bigger. For instance, this output is 0, and this output something like negative 4. But this one is the relative maximum, and this one is a relative minimum. So I usually, in general, we can't just cheat and skip past that step and take just whichever number has the largest output and think, oh, that must be the maximum. So other examples are cases where we have multiple kind of dips and things like that. So this relative minimum is actually higher than this relative maximum. That's not contradicting anything. It's just that this in its little area is a minimum, and this in its little area is a maximum. Okay, so we need some tests, either first derivative, second derivative, or confirmation from a graph to gauge whether these things are relative mins or maxes. That's it for this video. We'll be back in the next one for one final example to look at concavity in a function.